Hello everyone and welcome to Redstone Rocketry. Today I'll be covering the development and first full hold down tests of Vesta, my first thrust vector controlled model rocket. Vesta is built from a 56mm diameter cardboard airframe with a 3D printed chute bay and nose cone. The thrust vectoring mount uses two SG90 servos stacked on top of each other to gimbal the motor mount placed underneath. This is the 8th iteration of my TVC mount used on the last 3 hold down tests. While the previous iteration used a similar design, it did not have the accuracy needed, as you'll see in a moment. I designed the flight computer way back in late 2019 using the bps.space blip flight computer as the guideline. I decided to use an Arduino Nano and MPU 6050 with no barometer and instead just integrate accelerometer values to get an approximate altitude reading. While these components are a common choice to be used for a model rocket TVC flight computer, they are far from optimal as the Amiga 328P on the Arduino Nano is easily slowed down by the software needed to operate a TVC system, one major one being logging data to the SD card. The higher the software loop time, the lower the accuracy of the integration of gyros, accelerometers, and the iTerm in the PID controller. For this reason, the Arduino only logs sensor data from the gyros to decrease the loop time, and the rest of the data can be simulated after testing. After assembling the core components of Vesta, I decided to do the first hold down test using an Estes D12 motor. You will notice that the nose cone and chute bay were not included for this test, as the center of mass needed to be lower so that I could just use the TVC mount screw holes as an attachment point for the rocket to the test stand. Shortly after ignition, Vesta pitches over, maxing out the gimbal range of the test stand, and keeps their orientation for the rest of the burn. As I mentioned before, the TVC mount used in this test lacked the required accuracy to control the rocket properly, and so the mount locked up in a position that was not able to correct for the rocket's orientation. After this test, I designed a new mount with a slightly different layout that would fix the issue of the servos not directly driving the motor mount's orientation. Once this was printed and integrated into Vesta, I did a second hold down test on another D12. Unfortunately, this test looked similar to the previous one, but failed for a few different reasons. At this time I only had a 9V battery to power the flight computer and servos, as the LiPo hadn't arrived yet, and so shortly after ignition, the current draw from the servos browned out the flight computer, leaving the TVC mount unpowered for the rest of the burn. Once my LiPo had arrived, I assembled Vesta again, this time including the chute bay and nose cone, and headed out to do a third hold down test, this time using an Estes C6 motor, as I didn't want to continue wasting money on larger motors for these ground tests. After several failed ignition attempts, the motor finally ignited and Vesta began thrust vector control. This was the first time I was able to test the software with a motor firing, and so it wasn't too surprising to see it not perform well. The first issue was a typo in the integral gain limiter in the PID controller, which caused the rocket to think it was about 20 degrees off target on the y-axis. The second issue was the PID gains being tuned in a simulation with an incorrect servo-to-mount gear ratio. These issues could have easily been avoided had I done more thorough testing beforehand. When I was initially testing the PID controller, everything looked fine, so the typo was probably introduced during some last-minute changes that I didn't verify thoroughly. With these issues fixed, a few days later I set up Vesta again for its fourth hold down test on another C6. At this point I was fairly confident that I could fly Vesta and have it go well, but it is cheaper to do another ground test than lose the entire rocket. Finally seeing it work was a big relief, as I didn't want to be burning more motors on the ground instead of flying. As you can see, there were still some minor issues in the test, one being too much D-gain and a slightly misaligned TVC mount on the x-axis, but the y-axis was fairly stable. Another thing that may have contributed to the instability is the gimbaling of the motor applying small torques to the vehicle. With the issues from that final static fire fixed, Vesta should now be ready for its first flight. I initially planned to do this first flight on an Estes C6, but Vesta ended up being a little too heavy, and with a low apogee, the parachute might not even have enough time to deploy, and so the first flight will instead happen on a D12. Thank you for watching, and I'll see you next time.